Okay, I'm good. See you later.
You want to disclose?
Oh, please. Thank you, Kat.
The recordings are.
Okay, so we are now recording.
Okay. Is Mr. Feller in here or?
Yeah, he's there. His camera's just not on.
Okay. All right.
Yeah, I'm in here.
All right.
I am watching and listening.
Let me ask one quick question. So after the presentation, will I have a link I can send you of the recording? I mean, how do I?
Yeah, it should just pop up in the Teams, like in the chat somewhere, I believe.
Okay.
That's what it did last time, at least.
Okay.
Okay, so I am about to share my screen and then we can get started. Okay, and then let's present this slideshow.
I see.
You
Okay,
All right.
can you see that, Wendy?
Yes, it looks good.
Okay, all right, just wanted to make sure.
All right. Ready? We are the biosecurity barrier team from ECU Engineering, Capstone.
Hello, I'm Isa Alzigby.
Kelsey Bennett.
Tyler House.
Nick Baldwin.
And I am Tawana Warren, and again, we are the biosecurity barriers team working with the Lake Matamuskie Wildlife Refuge, and we are reporting to Wendy Stanton for this project. This is the presentation outline of what we will be going through and over today.
So starting with the project introduction, we're going right into Lake Matamuskie. Became a national wildlife refuge in 1934, and it's the largest natural lake in North Carolina, originating at around 100,000 acres, but then was drained for farming purposes to around 40,000. It's an average about 2 to 3 feet deep of marsh and cropland, and migratory birds, aquatic life, residential species, and recreational activities all go on at this location. Going into the vegetation loss, aquatic vegetation provide great habitat for overwintering waterfowl and bronze fish. But recently, well, over time, the water significantly declined due to an abundance of nutrients, which seems to be linked to the common carp that have posed a massive threat to that. They have around 4 to 5 million pounds approximately that are in there now due to them reproducing and coming into the less salinity waters at full speed and reproducing and just causing a lot of problems with the life that does occur there and algae blooms and etc. So right into the carp behavior, the feeding behavior of resuspension, top down, well, bottom up and top down feeding habits and excretion are all problems that occur with carp. And you can see here on this graph the direct carp impacts, which then go into how it affects the native fish and the bad algae blooms and everything comes to be with that. And here you can see the loss that has occurred is major from 1989 to 2017. And that's when they realized there's no aquatic vegetation at all there, which caused a huge problem. And that's what we're going to go into and how we're working on it.
Okay, the problem statement for this reads, primary carp gates proved to be ineffective during times of flooding and when maintenance is being performed on the primary gates. The buildup of debris at the Rose Bay Canal is also a main concern. With this project, we have a few constraints. The design budget for the project is $3,000 with a little flexibility where the more is needed. The carp barrier needs to be easy to maintain. It should extend 4 feet onto and above the adjacent land and must also have 2-inch vertical spacings to allow native fish passage while keeping out common carp.
So for the initial analysis of the current biosecurity barrier system, or current biosecurity barrier, the team visited Lake Matamuskie to the Rose Bay Canal to evaluate the primary gates and debris gate that's currently in place. After talking to Wendy, she said they have a 97% prevention rate against adult carp during standard water levels. They do maintain 2-inch vertical spacings across the canal. The debris gate seen in the picture below covers 3 out of 4 primary gates. However, debris buildup is able to occur on the 4th gate outside. They're made of aluminum, so plenty durable for the brackish water, and they are also easy to lift in and out of the lake with the 2 handles on top. Some of the ineffective features about the primary gates are that they leave carp passage unrestricted during high water levels or when water levels are raised above the primary gates. Additionally, they leave the passage unrestricted during maintenance operations when primary gates are lifted out of the water. Debris buildup is also a problem for the refuge as it can block the water flow into the tide gates, which can affect the head pressure on the tide gates, as well as the refuge workers are having trouble removing the debris from the canal with the current setup. Here are the Rose Bay Bridge drawings and models that we've created to outline the existing features there right now.
So here shows the engineering specifications for the design. So as you see, there's the primary customer requirements, which that falls under 3 categories. You got the basic, which is pretty much attributed needed in design, which is given to us by a sponsor. You got the performance category, which is the attributes chosen by a team that the sponsor would be happy to see and unhappy if it's not included. And you got the excitement category, which attributes the sponsor would like to see, but it's not necessary in the overall design. As you can see, some of the basic customer requirements is to prevent adult carp passage from entering the canal, which is pretty much with the whole design constraint 2-inch vertical spacings, and hopefully our goal is to get to that 0% passage of adult carp. Another basic requirement is to remove the debris from the canal, which is pretty much to gather all the debris in a centralized location for easy cleanup. And the third basic customer requirement is no passage of carp during flooding. And that's with the overflow barrier as it extends 4 feet above the current barriers and 4 feet adjacent to the adjacent land. And hopefully, the goal is to not allow any carp during the flooding. And then for the performance category, we chose reliability of the overall design and durability, so it can last for a while. And as performance categories state, we have that being aesthetically pleasing for the team, the tourists that go down there, so they don't feel like it's intruding in the overall experience. And you get the accessibility for the team, the sponsor, the crew, for the maintenance and such like that.
Moving into some of our solution methods, we began with stage 1 as the freewheeling method. The team basically gathered around and just started throwing out ideas on a whiteboard, pretty much spitting out anything that came to mind. We weren't going to, immediately disregard anything. So from this first stage, we ended up with a total of 20 design ideas. These were split up from the beginning for the overflow gate and the secondary gate. And then as we move along, we're going to, narrow these down even more. So for stage 2, we conducted a round robin method. We each took turns just going around and identifying what each group member thought would be one of the better alternatives. From here, we ended up with 10 total alternatives, 5 for each separate gate. And then for our final stage, we conducted another iteration of the round robin method, which led to the solution matrix shown on the right. So for the overflow gate, there are 5 solutions, and each of those 5 solutions can be paired with any secondary carp solution. So this gives us a total of 25 options moving forward. From those 25 options, we narrowed it down to 5 final designs. 3 of these designs utilize a stationary overflow gate. And then 2 of them utilize a sliding overflow gate. And for the secondary gate of the system, 2 of those used a pivoting gate, while 2 of them used the rate gate. And then we also have a bubble gate being used. Each of these final designs and features will be analyzed further and explained in the following slides.
So starting off the economic analysis, the first one we looked at is the overflow gate and solutions that we come up with. So for the first topic was the sliding gate that we looked at, and that would be above the primary gate. So for the flooding, 4 feet above that. And it would be made out of aluminum 6061 and have that frame and that track, and then the wire mesh would be there to keep out the carp. It would remain up in case of flooding, but if the first primary gate was being taken out for maintenance, it could also be a secondary barrier for that, where you can slide it down so that it will be the second barrier, like I said, and that would be utilized like that. And for the stationary gate that we analyzed, it would just sit on top of the primary gate full time and be there for flooding. And we looked at PVC pipe for that and lumber, as well for the welded mesh in between. For the sliding gate, it is a little more expensive because the aluminum 6061 is going to be used, because keeping it in water, it is the least corrosive, and it's good for that. And it also, like I said, is a secondary barrier if the first ones need to be taken out. But the stationary gates also would hold that purpose, that they could stay the whole time.
Moving into the analysis for the secondary carp gate, we had 2 models for this idea. The V model, which uses a bulkhead in the center of the canal to displace debris onto the 2 side gates where the debris features would be mounted for removal. And then we have the I model, which is just a single gate which goes directly across the canal as one piece. The 3 different material alternatives were used for both models. We looked at PVC pipe schedule 80, we looked at 6063 aluminum, and we looked at stainless steel. For the budget that we currently have, the stainless steel alternatives have been thrown out due to the high cost right now with the metal. Surprisingly, the 6063 aluminum have returned relatively good numbers as far as pricing as of right now, especially when evaluating that to the PVC schedule 80, which we thought would be less expensive than the aluminum. However, that did not turn out. So as we move forward, we're mostly going to be looking at the 2 second alternatives for the V model and I model.
So here it shows the 3 possible debris features that can be implemented in the secondary carp barrier. So we got the rake system, which pretty much goes across the barrier, pulling debris to one side of the canal for easy cleanup. You got the winch system, which uses a winch and some pulleys to pull the gate to the one side of the canal. And you got the bubble system, requires a power source and an air compressor and tubes to blow bubbles into the water, causing the debris to flow to one side. At this time, the bubble system is probably least likely to be considered due to that information. It could be possibly stolen or damaged and has a higher maintenance cost in regards to the other features.
We also conducted a risk analysis for each of our 5 final designs. This table over here on the left is kind of a synopsis of each of the risk events that were thought of for the final 5 designs. These risk events were ranked based off likelihood, impact, and detection difficulty. So, likelihood, a 5 would be it's very likely to happen. For impact, a 5 would be it's going to have a strong impact on the objective of the system. And detection difficulty would be whether or not it's hard to identify before it actually happens. On the right, we have a risk severity matrix. This just kind of gives a better visual representation of where these risk events fall in terms of whether they're good, bad, or, kind of in the middle. A majority of them fall in the yellow section, which is, kind of what we expected. We do have a few that are in the red that we're definitely going to have to just keep analyzing and keep an eye on as we move forward with whichever design we select.
So here shows design 1, which is a stationary overflow barrier with a secondary barrier, which is like the I model. As you see here, this is included a pivoting winch system. As you see on the secondary barrier has horizontal pulleys on both ends of, with a hinge on the rubber with some bearings to allow it to roll over to one side, and the winch will be on the far left, a little lower pivoting winch, so we can move from the barrier to one side for easy cleanup.
This is design 3 that uses the stationary overflow seen on the bridge to the left. For this model, I used the wood frame with the flattened expanded metal in between. And then for the secondary carb gate, this is the I model, which incorporates the debris rake. As you can see on the right-hand edge, you can see the claws. So for this idea, there will be 2 winches on the left closest to the road, and also a pulley on the other side of the canal, which will be used to, one will be used to pull the claw to the road, collecting the debris on the left, on the roadside, and then the other winch will in fact pull it back and reset it into position so it can be used again.
Here's also a model for design 4. Design 4 was a sliding overflow gate paired with the pivoting winch system for the secondary carp gate. As you can see here, the sliding gate was placed directly in front of the current rails that are in place. The model is shown with the gate in the up position, but just as soon as the primary gates were removed for maintenance purposes, this gate could slide down in the water so that there are 2 lines of defenses against carp at all times. The lower section is the secondary gate. Each of these taller 4 posts would have a pulley attached to the top that would be connected to the bottom of these 2 gates on the sides, and then that pulley would be operated with a winch system which would lift these gates up, and then debris could then fall onto the back side of these gates where it could be moved to the sides of the canal with a netting system. In the middle here, we have what we identified as the V model. It doesn't look like it, but this was a flattened expanded metal proposal, but due to just the SolidWorks computer system being ran on my laptop, I had to suppress that feature of it.
And here for the recommendations. Each of these recommendations were compiled using the 3 individual parts, the overflow gate, the secondary carp barrier, and the debris features. As you can see, the prices kind of vary. For the first design, we have a $4,360 cost. The second one, which is the stationary gate alternative 2, with the I model alternative 2 with the winch system, has a total of $4,990. The third design, which is the stationary gate with alternative 2, I model alternative 2, debris rate, has a total of $3,450. And finally, design 4, which is the most costly one. Yes, Wendy?
I have a quick question. On the winch system, I model alternative, when the system pulls the debris, I think it's alternative 2, that one, when the rake pulls the debris across to the side, up against that dike,
Right.
How would that debris come out? Will we need like an excavator, or how does that work when the debris is over to one side?
So once the debris is to one side, a refuge worker would have to scoop it out, but the debris will mostly be towards the bank side. So I would assume a rake could even be used just to scoop it out, as it should be too much. But as far as getting the big logs out and stuff, would probably have to require that in use to scoop it out.
Okay. Sorry to interrupt, but I was just trying to eyeball. I couldn't remember which alternative was what. You're doing an awesome job. Keep going.
It's fine. Okay, and for the design for which is the most costly one is a sliding gate with our first alternative. Our model alternative 2 with the debris rake has a $9,350 total cost. Due to the cost, solely based off of cost, it is the recommendation that design 3 is used, but nothing is set in stone, and it'll be further delved into when it gets back later.
So moving forward, we're obviously at the end of pretty much our semester's work. We think we're at the point for next semester that as soon as we get back, we can quickly identify our final design solution and then begin getting a detailed model of that solution and begin selecting parts and specific components that would have to be used. And then from that point, we hope to have to begin manufacturing and hopefully prototyping and installation by the end of next semester. So that is it. And if you have any questions, we'd love to answer them.
I think you all did a fantastic job on your presentation. I'm very impressed. Can we go back to the alternatives real quick? The pictures?
So this was the first one.
Okay. And that would also have a rake system, correct?
So this one would have, so for modeling purposes, it wasn't shown, but this one would also have the winch system. So this gate would pivot about this left side, and there would be a winch that could be used to rotate this gate to the side of the canal, which would concentrate the debris on that side of the canal. I guess it also, you probably were going to ask how the workers would get it out again. It also does not have a specific feature for that.
Okay. I really like alternative number 2 and this alternative, just off the, I'm thinking maintenance wise moving forward.
This one that's shown, or?
I like this one, design 3, I'm sorry, and then that other one where you have that gate that actually pivots.
This
the
one,
whole gate system pivots. The
number
one,
one?
I think that was this one.
Okay.
And those other designs are interesting too. I'm just concerned. It's nice having the debris come all to one side
Right.
of the canal, because but some of these designs, multiple designs could work on a different outfall canal, but it's just nice having it all directed to that one side so we can remove the debris with a rake or something like that.
Okay.
So I think as far as our debris features, we made them on the idea of concentrating the debris, not necessarily removing the debris completely out of the canal.
Which can be added in.
Which can be added in, yes. But that was the main objective, was just getting a concentrated. That way it's easier for you or anyone else at the refuge to just go to one spot and use like a shovel or a rake to get it out instead of having it scattered throughout the canal.
Absolutely. I appreciate that. And if it's not too much trouble to add in how much of a cost it would be to actually have the rake pull it up onto the dike.
Right.
That would be awesome. And then for like next semester or something.
Yeah, I mean, as long as it has something that it can slide on and maybe bring the rake up and onto the bank.
Yeah, I think
I mean, I think it's definitely possible.
Yeah.
It's just something that would maybe come in with a more detailed model. So.
Okay.
Definitely doable though, 100%. We can look into it.
I am really excited about all of these ideas, y'all. I can tell you guys put a lot of thought into this, and this is going to be so helpful as we move forward. And I'm excited about getting whatever you when you finish up the analysis, whatever design you decide to pilot on the refuge, I'm really excited to see how that works. This is cutting edge stuff, and you guys may want to go for a patent, right?
Maybe so. Am I still sharing my screen?
Yeah.
Okay. All right, Mr. Feller, do you have any questions?
No, you guys did a good job. If Wendy's happy, that's the name of the game at the end of the day. Yeah, the patent thing, though, ECU would get their cut out of it, though. so yeah. But anyway, good job, and if you guys got anything for me next week, just shoot me a quick email or hit me up on Teams.
All right.
All right. Be safe if you're traveling.
Same to you.
All right, Wendy, I guess if you just want to hit the stop recording button, and then the file should go somewhere automatically. So.
Okay.